This is a short video introduction to the paper Finite Sample Prediction and Recovery Bounds for Ordinal Embedding by Lalit Jain, Kevin Jamieson, and Robert Nowak.
The paper investigates the following problem. Suppose we are given a set of constraints in the form of distance comparisons between a set of items. For example, for a set of items A, B, C, D, and E, we are given comparisons like the distance between A and B is greater than the distance between A and C. The goal is to find an embedding of items in a low-dimensional Euclidean space such that the distances between points in the embedding agree as well as possible with the given constraints. Ordinal embedding is widely used to learn metric representations of human judgments and perceptions. For instance, if we ask people to compare the similarity of facial expressions, we can learn a metric representation of the visual perceptions of emotional expression. Ordinal embedding, also known as non-metric multidimensional scaling, was first studied over 50 years ago in the seminal works of Shepard and Kruskal. More recently, modern optimization methods have been brought to bear on the problem. Also, information theoretic bounds show that at least 2D n log n comparisons are necessary to learn an embedding, where n is the number of items and d is the embedding dimension. And the problem has been studied as the number of points become dense in the embedding space, and that embeddings can be accurately recovered in this asymptotic regime. This paper studies the ordinal embedding problem through a generative modeling framework. We suppose that there is a true embedding and a probabilistic model that generates noisy ordinal information. The key question addressed in this paper is the existence of a stable inverse for this model. It turns out that this is a subtle and tricky question, but using techniques from statistical learning theory and exploiting the special structure of Euclidean distance matrices, we are able to prove that the embedding that generated the ordinal data can be accurately recovered as long as the number of comparisons is at least dn log n, where again d is the embedding dimension and n is the number of items. For more information, please take a look at our paper. Thank you.